Now let's play with elimination and the half-lives. Here we should keep in mind first order kinetic, zero order kinetic. In case of first order kinetic, we have constant fraction eliminated, and in case of zero order kinetic, we have constant amount eliminated. Let me show you that half-life, it is a time when concentration decreases in 2 times. And actually, sometimes students are answering that half-life is 1 hour based on that, but it's not true, because here you can see 32 drop into 16. It looks like in 2 times. After that, have a look. We have from 16 to 8 in 2 times after 3 hours, right? Here we have 3 hours from 1 till 4. And from 8 to 4, we have 3 hours as well. So this confirms that half-life is 3 hours. And this portion of the graph, dropping of concentration from even greater than 32, we can't say exactly, corresponds to distribution phase. And after that, we have 2 half-lives, the first half-life and second half-life. And actually, yes, this corresponds to 3 hours. Good. This one. So once again, we have either 4 hours, yeah, or 5 hours. So have a look. From 0 to 1, we have drop in concentration twice. From 1 to 5, once again, twice. From 5 to 9, twice. But from 0 to 1, we have 1 hour, and from 1 to 5, we have period of 4 hours. And once again, this another representation of the graph, as we have distribution phase here. Distribution phase. So actually, half-life is 4 hours, because we have dropping from 50 to 25 and from 25 to 12.5. If we will use 1 hour half-life, this will not help us to identify, because we will not be able to check our hypothesis. And it is not a 5, because from 0 to 5 will be 5 hours, and from 1 to 5 will be 4 hours. So the correct answer is 4 hours. Next one. In this situation, to decrease plasma concentration in 50%, the half of the medication should be eliminated. And we can calculate initial amount of the medication or administered dose by using equation of volume of distribution. In this situation, we will multiply volume of distribution on plasma concentration. And initially, this will be 50 liters multiplied on 4 milligrams per liter. This will correspond to 200 milligrams. And when plasma concentration will be 2 milligrams, this will correspond to 100 milligrams. So 100 milligrams of medication should be eliminated, right? So 200 minus 100 milligrams. And we have elimination rate 2 milligrams per hour. If we will do a timeline, and here we'll put 200 milligrams, each hour concentration will, or amount of medication will decrease on 2 milligrams. So next 2 hours, we will have 198, 196, 194, 192, 190, etc. How to calculate how long does it take? We should actually divide this difference, or 100 milligrams, to elimination rate 2 milligrams per hour, and we are crossing milligrams and getting 50 hours. Okay, good. Next one. So we have those 240 milligrams, volume of distribution 30, half-life 4 hours, first order elimination, serum drug concentration just before next dose 8 hours later. We are looking for plasma concentration in 8 hours. We can use volume of distribution equation, so it will be dose over plasma concentration. And we need to find the plasma concentration. And initially, plasma concentration will be dose over volume of distribution, and will be dose 240 milligrams divided on volume of distribution 30 liters. And this will correspond to 8 milligrams per liter plasma concentration. The question is asking about plasma concentration after 8 hours. So we have timeline. Once again, let's do that. And initially here we have 8 milligrams per liter after 8 hours, and half-life is 4 hours. So we can assume that we have 2 half-lives, right? One half-life and second half-life. So after one half-life, plasma concentration will be 4 milligrams per liter, and after 2 half-lives will be 2 milligrams per liter, which is the correct answer. Next one. 6% of steady state level. So time. Did you remember this table? 6% of initial steady state level. This corresponds to 4 half-lives. We need to multiply 9 hours on 4 half-lives, and we get in 36 hours. Half-life 3 hours. What percent of initial dose will be 6 hours later? So percent of initial dose 6 hours later. Easy, right? So 1 half-life 50%, 2 half-lives 25% will be from initial dose. What about this question? So what we have here, we have 500 milligram IV. So bioavailability is 1. Plasma concentration 12.5 milligrams per liter. Plasma concentration after 2 hours 10 milligrams per liter. Assuming the drug is first order elimination, which of the following will be the serum concentration of drug X in next 2 hours? So in next 2 hours, plasma concentration next 2 hours. Let's do a timeline, right? We have initial dose of 500 milligrams here. After that, we have immediate plasma concentration at this time, 12.5 milligrams per liter. And after 2 hours, we have plasma concentration 10 milligrams per liter. The question is asking what will be the plasma concentration at this moment of time after 2 more hours. You see that we have elimination by first order kinetic. That means that we can operate with term half-life, volume of distribution over the clearance, but we do not have volume of distribution here. We do not have clearance, and even we do not have half-life, right? We do not have a half-life, but we know that we have first order elimination. You should remember that first order elimination, it is a situation when we have eliminated constant fraction, not amount, but constant fraction. Which fraction eliminated in this situation? 12.5 milligrams per liter minus 10 milligrams per liter divided on 12.5 milligrams per liter. And actually, we have eliminated 2.5 milligrams per liter in terms of concentration, right? So it will be 2.5 milligrams per liter over 12.5 milligrams per liter. What is the fraction? 0.2. What does it mean? It means that 20% eliminated. So what happens next 2 hours? Next 2 hours, we will have elimination of 20% as well. And plasma concentration will drop on 20%. And 20% from 10 milligrams per liter, it is actually 2. And plasma concentration will be 8 milligrams per liter. You can solve this question by doing next calculation. This is one way, yeah, how to do that. Another way how to do that, we can find volume of distribution. It will be dose over plasma concentration, and initially it will be 500 milligrams divided on 12.5 milligrams per liter, and it will be 125 to 50, 40 liters. As we're crossing, will be 40 liters. We know that volume of distribution is constant, and for next 2 hours, actually we can find dose remaining in the organism. Yeah? As we know, volume of distribution is 40 liters. How we can find this dose? We should multiply 40 liters on plasma concentration 10 milligrams per liter. And this will correspond to 400 milligrams. After that, we can subtract 500 milligrams minus 400 milligrams. We're getting that 100 milligrams eliminated during 2 hours. Actually, this will correspond to 20%. 100 over 500 will be 0.2 or 20% eliminated. So next, here we had 400 milligrams, and the next 2 hours, 20% will be eliminated. So 40 plus 40 will be 80, and the remaining dose will be 320 milligrams, right? Because 20% of 400 milligrams. It will be 320, and we can find plasma concentration. So in this situation, plasma concentration will be dose 320 milligrams divided on volume of distribution 40 liters, and this will correspond to 8 milligrams per liter. So this is another more complicated way how to solve this task. All right, next one. Serum drug concentration is 16, plasma 16 milligrams per deciliter. If drug follows zero order elimination kinetic, what is the serum concentration be in another hour? So zero order elimination. And the question is asking about plasma concentration another hour. Once again, timeline at the beginning, 100 milligrams, 20 milligrams per deciliter. After 1 hour, we're getting 16 milligrams per deciliter. Zero order elimination means that constant amount eliminated. And here we have elimination of 40 milligrams per liter, right? 20 minus 16. That means that next hour, we will have elimination of the same 4 milligrams per liter, and this will correspond to 12 milligrams per liter, per deciliter, sorry. Because of zero order elimination. And the answer is 12 milligrams per deciliter. Okay, now what about that? Drug A and B. Yeah, so we have clearance for drug A equal to clearance for drug B, and metabolism of drug A equal to metabolism of drug B, and volume of distribution for drug A 10 liters, volume of distribution for drug B 30 liters, half-life for drug A 60 minutes. And the question is asking what is the half-life for drug B? How we can calculate half-life? Half-life, it is a 0.7 multiplied volume of distribution over clearance. And what we have? We have volume of distribution, right? We have half-life of drug A, and we need to find the clearance. So clearance will be calculated as a 0.7 volume of distribution divided on the half-life for drug A, and this will be clearance for drug A, volume of distribution for drug A. And it will be 0.7 volume of distribution for drug A, 10 liters, over half-life for drug A, 60 minutes. Or it might be 1 hour for a simple calculation. It will be 0.7, 10 liters over 1 hour, and it will be 7 liters per hour. So the clearance for drug A, 7 liters per hour. Clearance for drug A, 7 liters per hour. And we know that clearance of drug A equal to clearance of drug B. So clearance for drug B, 7 liters per hour as well. What is the half-life for drug B? The half-life for drug B will be 0.7 volume of distribution for drug B divided on clearance for drug B. And this will be 0.7 volume of distribution for drug B, 30 liters, over clearance for drug B, 7 liters per hour, right? So what is the answer? 3 hours, or around 180 minutes. 180 minutes. What about that? Volume of distribution 40 liters and clearance 2 liters per hour. 2 liters per hour. Which of the following is like a half-life? Half-life 0.7 volume of distribution over clearance, and it will be 0.7 40 liters on 2 liters per hour, and that will correspond to 14 hours. Good. Next one. What about that? 30 milligrams once daily. 30 milligrams, and tau, you see, once daily. So tau will be 24 hours, 1 time daily, 1 times per day, yeah? Daily. Volume of distribution, 30 liters. Clearance, 0.15 liters per hour. So what is the half-life? We're looking for the half-life. How we can calculate half-life? Half-life 0.7 volume of distribution over clearance, and it will be 0.7 volume of distribution. We have 30 liters divided on 0.15 liters per hour. It will be 200 multiplied on 0.7 will be 140 hours. We do not have hours, we have days, and we are assuming that 1 day, 24 hours, and we need to divide 140 over 24, and this will be 5.8 days. So this is the half-life.